So you're going to miss that. The title, once again, so it's on the expressive power of nonlinear merge and shrink representations, and I'll kind of start with a kind of disclaimer. If you hear merge and shrink, then you probably think of heuristics, like heuristic search. This could be interesting to you, possibly, even if you have no interest in heuristics at all, because we think that what this is really about, the kinds of representations that are used by these merge and shrink heuristics, can be used for all sorts of things. So if you don't like merge and shrink heuristics, but maybe you like something like BDDs, this could be quite interesting. Of course, the flip side of that is if you're very interested in heuristics, this might not be relevant to you anyway, because it's not really focusing on that. So I want to start with kind of a short version of the result, like why we did it and what we did. And once I've basically told you the full story, go a little bit into some of the details. So merge and shrink was devised as a way of deriving heuristic estimates for optimal state space search by Röger, Finkbeiner, and Podolsky in 2006. And for the most part, people have focused on a particular subclass of the merge and shrink framework, which we call linear merging. So in planning, basically, people did only linear merging until 2013. There was a technical and also kind of theoretical reason for that. We didn't really understand the nonlinear merging well enough to implement it efficiently. That changed in 2014. Since then, there have been 3 different papers that focus on nonlinear merging. So there was one by us, basically, that used an old merging strategy suggested by the original authors of merge and shrink. There was some work by others as well, and another paper by us that kind of used symmetries to inform a nonlinear merging strategy. So this seems to be a topic that is now kind of becoming a bit more interesting. And that kind of raises some theoretical questions, because linear merging strategies were quite well understood. So we kind of knew very well what they did, more or less since the start of merge and shrink in planning. So Bly Bonnet observed, this is kind of not a paper reference, it's just like an oral communication, that the representation used by merge and shrink heuristics, if you have a linear merge strategy, is essentially a binary decision diagram or an algebraic decision diagram, so if you want to make things a bit more complicated. If you don't know what that is, it's a very, very common representation used, for example, in model checking for compactly representing, let's say, propositional formulae, something like that, or rather their models. And that's quite exciting because it tells us a lot about what we can and what we cannot do with merge and shrink. For example, there was a paper at ICAPS a few years back that showed that for certain kinds of problems we can solve them optimally in polynomial time with merge and shrink, and with linear merge and shrink in particular, and you can only possibly do that if the problem you're solving can also be compactly represented with a BDD, because we know there's this relationship. Another reason why it's interesting is because it connects like this explicit state heuristic search thing to symbolic search, which is kind of traversing state spaces with the aid of BDDs, which is a very successful technique in model checking in other areas. And that actually gave rise to a combination of kind of merge and shrink and symbolic search by Stefan Edelkamp, Peter Kisman, Alvaro Torralba, and others. That gave rise to the extremely successful Simba planner, or Simba star planner that won the optimal planning track of the last IPC, and this is general excellent work. So what we see here is kind of some theory giving inspiration to practice, but this is all linear merging, right? So what's going on with the non-linear merging? So an obvious question to ask there. So if we allow like kind of this kind of general thing, we drop the restriction, can we do things we couldn't do before? And if the answer would turn out to be yes, well, it would certainly give us an incentive, or at least some good motivation to look more deeply into, what are good nonlinear merging strategies, kind of what is the space of options there, what can we do there, and possibly even because of kind of the relationship between linear merge and shrink and BDDs, give us something better than BDDs for symbolic search. And that's not really a pipe dream. I mean, people kind of who care about BDDs and symbolic search have actually looked for something exactly like that, which almost exactly generalized BDDs in the way that the nonlinear merge strategy is generalized to the linear case, with something called sentential decision diagrams. And there's really a bit of a race out there kind of to use techniques like that to really push the envelope in that area. So there's been a series of papers by Adnan Darwish. He's coming up with efficient implementations now as well. So there seems to be something interesting out there. But all this is only really going to be interesting if it turns out we can actually do something with the nonlinear ones that we can't do just as efficiently with the linear ones. And initially we actually thought that would not be the case. Initially we thought, linear is as powerful as it gets. So in this paper we answer the question. So the answer is yes, it is more powerful. And these are the results. Basically what we show is if you want to have a general representation, so you have something that requires n bytes or something like that in the merge shrink framework, and I force you to turn it into something linear, you will have a super polynomial blowup or at least the conversion technique that we give you can only give you kind of this bound, n to the power of theta of log n, and it's kind of an interesting bound. It's not exponential, right? It's not 2 to the n or anything like that, but it is super polynomial. That's larger than any polynomial. It kind of grows deceivingly slowly, but at the end it's actually going to kill you, because if your n is something like 10, something like 1,000, which is not a lot for the size of representation, you'll end up with n to the 10, which is not something you can afford in a translation. But that's just like the first result just says, okay, we can convert it with this blowup. It doesn't say that the blowup is really necessary. So we have some more fine-grained results as well. One of them is actually that instead of just saying, there's this log n in the exponent, we can tell you something more precise, which depends on just how nonlinear you are. I'll make that. I'll give you the details of that in a few minutes. And also we showed, and this is the really exciting part and the part that was quite difficult to prove, but also I think we had a very, very nice proof. You cannot possibly avoid this blowup. So it's not just that our conversion routine somehow doesn't come up with a good variable orderings or something like that. It's just that it's impossible to come up with something that is more compact than this n to the theta of log n. Okay, so that's a short story. We have a few more minutes. I can tell you a little bit more about how this actually works, and I'll start by telling you a little bit of what these things actually are, what these merge shrink representations actually are. So I'll first tell you what they're used for. They're basically data structures that allow you to compactly represent functions, namely functions that are defined on assignments to finite domain variables. So for example, these can be truth variables, so you have something that maps assignments to truth variables to something else, and that would actually be what a BDD is, right? A BDD takes assignments to truth variables and maps it to either true or false. So one thing you can do with that, the example given at the bottom, is you can use a merge shrink representation to represent the set of models of a formula and propositional logic, and this is what BDDs do. But your variables can also be, they don't have to be binary. They can be kind of finite domain. Maybe what you want to do, for example, is represent the solutions of a constraint network. There's also something you can try to do with that, and then you can efficiently do things like counting the number of solutions. But of course, the original use and the thing that we've been using them for is to represent heuristic functions. So in that case, the variables you're using are just the state variables of a planning task, and the function is the function that maps the assignments to these variables, so the states, to your heuristic estimate. And I'll show you kind of what these things look like by showing you how to represent a particular kind of simple, but in this context quite important little function. So for this I have to take you back to Algorithms and Data Structures 101. I hope you remember heap sort. Because what we want to write down a function that checks the min heap condition. So what does this mean? Well, we make it simple, right? We'll check if like a sequence of 3 numbers, v1, v2, v3, satisfies the min heap condition. The min heap condition for like a complete tree like that always means that if you have a number somewhere, it must be less or equal to its 2 children. So if we look, for example, at the now it would be nice to have the pointer. But if you look at the middle picture, you can't see the mouse pointer anyway. Okay, the 1 is less or equal to 4. Is also less or equal to 2. So the second heap there the second tree there satisfies the heap condition, the min heap condition. The one on the right hand side does not, because 3 is not less or equal to 2, right? So if we want to write a function that checks this condition, of course it's a function which takes 3 inputs, In our case, we want these inputs to be numbers between 1 and 4 because we want a finite domain. So it will take these 3 inputs, map that to either true or false, and specifically it will be the function shown at the bottom that takes as inputs v1, v2, v3, and it will give you true if the first variable is less or equal to the second, and if it's less or equal to the third. Otherwise, it gives you false. I hope this is all fairly clear. And okay, so now we have a function. It has kind of 64 inputs. We could represent it as a table with kind of 64 entries, but if we have not 3 variables but 100, that's not going to work. So we want a compact representation for that. And here's basically how a merge and shrink representation for that function would work. What a merge and shrink representation essentially is, well, you start with a binary tree over the variables. So all the variables occur exactly once at the leaves. So in this case, we have v2, v3 at the bottom, v1 at the top. We get to choose how to arrange the tree. Then one thing you have is at each of the leaves, you have a little table that basically can map the values of these variables to something else. Here it's all just identity mapping, so you can basically completely ignore that. And then the exciting part happens at the internal nodes. We call these the merges. They basically tell you how to combine values that are propagated up from the children to a value for this inner node. And it's best explained by an example. So if we want to evaluate what happens with the input 1, 4, 2, so v1 has a value of 1, v2 has a value of 4, v3 has a value of 2. Well, what you do is you basically look at for example, at the table for v2, and the 4 is mapped to 4 by that table. For v3, the 2 is mapped to 2, so we have a 4 and a 2. And we take that and go to this merge and look at the entry for 4 and 2. Okay, it's the one highlighted in red. It's the number 2. And actually, mathematically, what this table does in this case is compute the minimum of those 2 values. So we have that. It's kind of an intermediate result. It kind of summarizes all we need to know about variables v2 and v3. And with that, we can keep going. Look at variable 1, which basically has a value of 1 here. So for the table at the root, we take as an input the 2 that we get from the left child, from the merge, and we take the 1 that we have from the right child, the variable v1, and in the table for the root, that maps to true. So the output is true. Does this all make sense? Because that's how merge and shrink works. Okay, the people who've written the original merge and shrink paper are nodding. Not all the others are. Okay, but it's really quite simple, right? You feed the values for which you want to evaluate to the leaves, and then you basically use these tables at the internal nodes to compute a new value out of the values you get from your children. Another example would be 3, 4, 2. So what changes here is that the input for variable 1 is no longer 1, it becomes 3. So this table now we've highlighted the 3, which means that at the table at the top we have to go to the 3rd column rather than the 1st column, and then our output is false, right? And the question I want to ask is not how to find these tables so that I get a given function or something like that. That's someone else's duty. The question is, which kinds of functions can we compactly represent with this kind of representation? So in general, you will have many variables, and they'll always be arranged into a tree like that. And the value you compute is always the one you kind of get at the top at the end. Okay, how am I with time, Christian? Okay, excellent. So the representation size, basically, of this thing is just the number of table entries. And if we generalize this thing to something which has more variables but still represents the heap condition, what we get is basically something on the order of n to d squared, which, as you notice, is polynomial in the number of variables. So it's only polynomial in the number of variables. And even though all functions can, of course, be represented like this, because basically you can just make larger and larger tables, we're really interested in things that can be represented compactly. And that means a polynomial bound. And basically, if you take the example and generalize it to larger kinds of heaps, you can show that you can actually compactly represent all heap predicates. Why are these compact representations important? Well, if something is small, basically we can process it quickly, so it's important for polynomial time algorithms. Now, the main question was, what about linear versus non-linear, right? So what is actually a linear merge and shrink tree? A linear one is one that looks like the one on the left, where basically you only merge something with a leaf. And the nonlinear one is something that doesn't look like that. Now, the linear ones very much work like BDDs. They're essentially just a different way of writing down a BDD. And the question for us was not just what is linear, what is not linear. The question was more like kind of how linear is a given tree. So the thing at the left is definitely linear. The thing at the right definitely isn't linear. But the thing in the middle is kind of, you know, somewhat linear, but not quite, right? So maybe we can come up with a quantitative measure for that. And actually, such a measure already existed, invented by someone who was looking kind of at the size of rivers and, you know, rivers flowing into other rivers and kind of how large is a large river. So it's a measure of linearity. And because we're a bit short of time, you have to look into the paper to see how it works. But basically, what it gives you is for a linear tree, it will always give you a value of 2 as kind of its Horton-Strahler number. That's what it's called. For a complete tree, it will always give you the logarithm of the number of variables, or equivalently the number of layers. And for something in between, you get something in between. And okay, so I'm getting to the things we actually proved. So there's first the good news. The good news is you can always compile a general merchant string representation into a linear one, and the blowup will not be terrible if you're kind of somewhat linearish already. So what it says here is for every merchant string representation, we can come up with a linear one, and the exponent by which the size will explode is only this Horton-Strahler number of the merge tree. So if your thing is kind of close to linear, let's say that thing is bounded by a constant, that will actually be polynomial. However, it will not be always bounded by a constant. So in the worst case, where you have actually a complete tree, you end up with this log n exponent that we saw before. So this is one particular compilation. Maybe there are better compilations. And the answer, of course, is no, there aren't. So that's the bad news part. There exist family of functions where we cannot do better than what we just saw. And this is the really, really exciting part about the paper, especially since it's a really, really nice proof, I think. And that's why I bored you with the heap predicates in the first place, because the heap predicates are exactly the ones that show this. So the heap predicates, as I told you, as we saw, can be represented compactly with general merchant string representations, but the core proof in the paper is that this is not possible with the linear ones. So if I have a linear representation, think of it as a BDD. I can pick any order of the variables. I can, you know, do them in any order I want. I will not be able to represent these things with polynomial size. I will need a number of BDD nodes or a number of table entries for merchant string that will grow as at least as something like n to the power of the logarithm of the number of variables I have. And that's basically all I wanted to say. So to conclude, I kind of say what I already said before. The general representations are more powerful than the linear ones. We have two results, an upper bound and a lower bound. You can be quite fine-grained by looking at this measure of like linearness of a tree to kind of see just how bad the blowup will be. And given the result, I think there's quite an incentive to look more deeply into these nonlinear merge strategies, and maybe even to be a bit more ambitious and try to use this to kind of marry this idea of nonlinear merchant string representations to the idea of symbolic search. And with that, I'm done, and thank you for your attention.